I'm so thrilled with the energy in this room, and I really hate to stop the conversation, but you will have all day to be networking and connecting. So good morning from everybody around the world. I understand we have 12 countries represented here in addition to the US, so welcome from all corners. Welcome to MIT alumni, to faculty, to staff, to students and friends. This is just an incredible event. Natalie Lorenz Anderson is my name. I'm the class of '84. I was course 6. For those of you who know the numbers, you know it's electrical engineering. For those who don't, you still now know. I'm also the Alumni Association president this year, and it's quite an honor to be able to welcome you to this conference. I was fortunate to participate in versions of women's conferences years ago, but it's been quite a while since we were all together like this, so this is amazing. And a big thank you, by the way, last night for those who were involved in the reception. A big thank you to the MIT Club of Boston and Amita. That was an incredible event at the MIT Museum. We heard some inspiring words from Megan Smith, and my brain tried to process them overnight, but I'm still working on all of the possibilities for us. And one of the things that she reminds me of in her remarks about all the amazing women that have come before us and are still with us, that are doing incredible things, is that it reminded me of something I said last fall at the MIT Alumni Association ALC, or Leadership Conference, about planting the garden, right? And I believe today is another step. It is spring. This is our garden of amazing people in this room, and each of you is going to go out and do amazing things with what we're talking about today. So I mentioned that I've been involved, or at least attended, other conferences. There have been several conferences on the Alumni Association and on the Sloan side of this, and other parts of the Institute, frankly. Today's conference really continues that proud tradition and brings us together for amazing sessions that I think will help you feel the warmth of this community, this supportive community, the brilliance of MIT women and our friends in our MIT orbits. And I think when it's all said and done, you will have experienced what we like to say when we graduate from MIT, the fire hose of inspiration, but also of education and of celebration. Many of you, but maybe not all of you, know that the Alumni Association has prioritized in our strategic plan engagement of MIT's alumni as a strategic goal. And as I've said before, MIT Sloan has also been hosting and sponsoring Women Connecting through their women's conference for many years. So as such, it made sense when a couple of years ago, we decided to join forces and bring together the whole of our ever-growing alumni community. So I want to pause and offer my gratitude to MIT Sloan and MIT Alumni Association for the work on creating this important special day, and special kudos to Kathy Hawks with Sloan, Whitney Espick with Alumni Association, and then, of course, all of the incredible people on these teams that helped put this together. So thank you to all of you for this. I also want to acknowledge our conference sponsor, the Anchor Point Foundation. They are the ones that made this conference event possible. And I'm really pleased that we have the interim dean of the MIT Sloan School of Management, Georgia Parakis, with us in the audience this morning. Thank you, Dean Parakis. And thanks to everybody who made this happen today. So while the plans for the conference started a year plus ago, I know that many of us in the room are likely feeling that there is no better time for us to be having this conference. It's a significant time in our world. I don't need to enumerate the challenges that we're facing across multiple fronts, some recent, some decades long, some centuries long. Some are systemic, and some impact us to our very core as individuals. And all I can say is that I can't think of a better time than now to be gathering with an incredible group of people in this room. Each of us chose to be here because we're a part of this community that's forever focused on solving and fixing and advancing. And in good MIT nerdy spirit, I went back last night and kind of looked up community, because I also thought about the word unity. And I wondered, well, are they connected? So what I learned is that they kind of are, but not really. From the Latin community, it really has the origin of com, or coming together, and munis, performing services. Well, that feels pretty relevant right now. The word unity really is a different origin, and it really relates to one. But then I found Scott Monty from the Franklin Matters blog, which is here in Franklin, Massachusetts. I love how he put it all together when he thought about those two words. And he said, people collaborate to create something bigger, better, and stronger. And that's what community and unity can do for us. So I just wanted to add the little nerdy, almost midnight musings. So we are further united, mind, hand, and heart, as alumni, students, faculty, staff, and friends of the Institute. We share so much already, and we should celebrate those bonds. And yes, today also provides the opportunity for us to connect, to network across the diversity of our experience as well, our disciplines, our careers, our identities. Those of you who have heard me speak about my hopes and dreams as the president of the Alumni Association this year know that one of my themes is to meet alumni where you are. So while I'm pleased that you all are here physically, it's also to meet you where you are in your lives, what matters to you, what you're working on, what your hopes and dreams are. So I hope today that as you're learning and developing, you'll ensure that you expand your community and continue that progress. Make the most of your time to build connections. And it means not only reconnecting with classmates and friends, but it also means going up to people that you've never met before and saying, hey, my name is Natalie. I'm here because I want to meet more people, or I want to learn something about something else. So try to connect with alumni from other generations, different stages of life, different careers from your own, and in different industries and disciplines, so you can leave knowing more about the amazing peers in your network. Last night, I felt that way. I ran into so many different people I had never met before and learned so much about each of their stories. And in fact, one of those conversations was, in fact, etymology, or the study of language. And so it was kind of amusing last night thinking back to that as we had discussed Latin and Greek and how it plays into our language. So I'm learning along with all of you. And beyond the professional and educational ties, don't forget, this is a supportive network to help us tap into and lead across all dimensions of our lives. So as I say the word lead, I want to mention that Sally Kornbluth, our president, would have loved to have been here today, but unfortunately, she was unable to join due to unavoidable scheduling conflicts. I know you can imagine what life is like for her right now. So I wanted to say that as a champion of our community, she has sent along a special message. Please roll it.
Hello, everyone, and welcome to the 2025 MIT Women's Conference. I'm thrilled that you've made the time to attend this fantastic event. I've taken a look at the program, and wow, from human health to biotech, entrepreneurship to space exploration, you'll be hearing from an incredible array of speakers immersed in research on the very frontiers of knowledge. I haven't been at the Institute for all that long, but from day one, I've benefited enormously from the leadership of many exceptional MIT women. To name two I work closely with, there's Paula Hammond of the class of 1984, who also earned her PhD here. Today, after almost 30 years as a professor of chemical engineering, she serves as MIT's vice provost for faculty. Her scholarship and her character have also earned her our highest faculty rank as an institute professor, and she was recently awarded the National Medal of Technology and Innovation. And then there's Cindy Barnhart, a double degree holder who earned her PhD here in 1988. While serving the Institute for 4 decades as a distinguished faculty member, she has also served as chancellor and as provost, only the second person in MIT history to have been selected for both of those roles. I've had countless opportunities to appreciate their hands-on approach to challenges, their talent for rigorous analysis, their wisdom and insight, and their incredible humor and heart. And I see these very same qualities over and over again whenever I meet MIT women in any field, anywhere in the world, women like all of you. I want to thank the Alumni Association and the MIT Sloan School of Management for hosting this conference, and the Anchor Point Foundation for their sponsorship. And thank you for being here to innovate, collaborate, and connect. Enjoy the day.
From day one, Sally has talked about the importance of alumni in general, and alumni in her world, in her role for MIT. So you know you have a champion with her, and she's just been wonderful for us. So without further ado, let's get into today's program. I'm delighted to welcome as today's MC, Adela Jamal. For those of you who have not had the pleasure of meeting Adela, she's co-founder and manager at Milemark Capital, a venture capital firm focused on applied AI startups led by diverse teams out of innovation hubs like MIT. And yes, that includes backing incredible female founders, which is yet another one of my dreams as the Alumni Association president, is for us to continue to work on that ecosystem. As a further testament to the capacity of our MIT community to connect on our shared values and desire to make an impact, Adela co-founded Milemark with her peer MIT alums. She's an angel investor, an advisor, a mentor, and a fierce champion for women. She's also served on the Sloan Women in Management Board, Sloan Fellows Women's Council, All Raise board member. That board, or that All Raise, is focused on elevating the next generation of female funders and founders, which is really important at our time in our world. She's a current AMITA board member as well. Her diverse personal and professional background has given her fantastic opportunities to work in both the US and India. Her journey spans working with early stage tech startups in Silicon Valley, consulting with Fortune 100 companies, serving in executive leadership roles at Sony Pictures, and launching global platforms to empower underrepresented communities. Adela is originally from India and was raised a global citizen, shuttling between the US and India. Adela credits her international background for providing her with a unique perspective on what it means to be a woman in this world, especially the business world. And that has fueled her passions to be a tireless advocate for fostering equity, equality, innovation, leadership, not only in entrepreneurial ecosystems, but in each of our communities. We're very delighted to have you with us here today. Welcome, Adela.
Well, good morning, everyone. Phenomenal, turnout. Great to be here with everybody. And also just want to acknowledge that it's easy for all of us to show up and be here for a very, bright and early start. But I know that everyone has traveled actually from around the world to be here. So thank you for putting this event at the forefront of your schedule and also just coming together with the community, which is so important and a big part of what we stand for. So first of all, a big thank you to Natalie for that wonderful introduction. And also a big thank you to MIT President Sally Kornbluth for her phenomenal video message. Sorry she could not be here with us today. Also, before we get into the fantastic day and numerous breakout sessions, I also want to acknowledge the association here, the entire team behind the scenes that put together this event. Not a very easy feat. So thank you so much to Greg, Riley, Amy, and the entire organization. For me personally, being here, supporting MIT, being a part of the numerous women's initiatives under the umbrella of MIT is really what sort of drives me. I have, I think, taken on many roles in my career over 20 years, but really coming back to MIT, working with the team here, and also just thinking about, what each of us needs from resources, support, relationships is truly what sort of drives me. So to be here with all of you is truly an honor. As Natalie mentioned a moment ago, these days I'm actually focused on running my new firm, and it's also focused on supporting, investing in diverse teams and supporting the MIT community. But really, it's also the other activities. So being on the AMITA board, and I see a lot of the board members here today, that is truly what fuels me being here in front of all of you, and also just providing that support, not only for our peers, but for that next generation of women is truly important. So for today, even though we have a whole phenomenal lineup of sessions and breakout sessions, we really want to just highlight that we hope everybody here will say hello to, who's on your left and right, get to know the community, get to really enjoy the fact that this event is highly curated. People have come in with all types of backgrounds and focuses, really try to foster those relationships, because I can say I travel all over the world, and to actually have a room like this is really powerful. This is real community, and we really want you to leverage and actually grow from the events and the conversations today. I also like to just call out that, before we continue, unfortunately, I think for the most part, have all heard the passing of David Schmidtlein earlier this month. And he was actually the MIT Sloan Dean from 2007 to 2024. Many of us in the room actually, I think, have worked with him or actually been under his leadership. I personally was here as well at Sloan while he was Dean. And he's actually a massive part of, not just his role as dean, but also the alumni, and has done a ton. So, in addition to being MIT's longest serving dean, he was also a massive champion for the MIT Sloan Women's Conferences in 2017, 2019, and 2022. And we will certainly be missing Dean. But I really have heard actually from a number of people in prior conversations that, everyone is really excited to continue his community, his work, his efforts in the years ahead. So, turning back to today's program, it is a packed day. So, I hope everyone will fuel themselves, enjoy the coffee and the refreshments. A little bit of sort of housekeeping. We will be using this room as the main room for gathering and addressing our main stage sessions. We're going to be having the lightning talks kicking off in a moment. And we're also going to have additional breakout rooms, which will be happening on the second floor. So if you are here for registration and breakfast, just keep in mind that we'll be using both areas. And then during lunchtime, we are very excited because we're going to be having an exciting keynote. And we're also going to be talking about AI in the workforce, which of course is something that we cannot avoid. And we're also going to be having just a slight adjustment to our schedule, which is that we were hoping to have MIT Sloan's Renee Richardson Goslin, but she is unable to be with us here today. She will certainly, hopefully join us in the future. But we're going to continue the conversation, the theme, which is really going to be around AI, talking about workforce, talking about how it impacts our professional lives. And we're actually very fortunate that MIT alumna Elizabeth J. Altman, LGO 92 and SM 92, Associate Professor of Management at the University of Massachusetts Lowell, she will be joining us today. So we're very, very happy to have her and really appreciate her jumping in last minute. During her talk, Liz is going to actually explore what's happening with AI, the workforce, talking about the evolving role that we have to deal with AI, reshaping strategies in organizations. And we're really enjoying the fact that she's going to come in, and then also we will lead into one of the main sessions, which is going to be fantastic, having Natalie discuss with Linda Henry, who's an SM05. And Linda, if you haven't actually had a chance to meet her or to interact with her, she's very active in the Boston scene. She's actually led across various industries. She's done a lot with the entertainment industry, being a Emmy-winning documentary producer. She's also very actively involved in the professional sports leagues, especially here in Boston. She's also a partner in the Fenway Sports Group, which includes the Boston Red Sox, yes. And she brings a very unique perspective on her leadership in media, civic management, community activism, and innovation. So it's a tremendous honor to have her here with us. Moving forward, of course, we're going to have various talks and a lot of different discussions and different topics, hopefully very relevant to everyone who's here with us. But again, we just hope that it's going to be, fostering great conversation. Before we head into our first session of the morning, we are going to be using a little bit of technology. So I think as everybody has seen, there are QR codes on your tables. We're going to have you actually scan that so we can have an interactive Q&A. You can actually submit your questions through the QR codes. Just open up your phones, take a picture, submit your name, and we will be actually managing that up here. So without further ado, I'm very excited to introduce you all to our first session. Please join me in welcoming a very impressive trio of MIT alumni. They're actually faculty who are currently exploring cutting-edge breakthroughs in human health science. And we're going to be doing this in the function of rapid fire, sort of lightning talks, as we call it. So we're going to be learning how the MIT faculty are advancing health outcomes, developing ethical AI, very relevant right now, focusing on healthcare, and also using digital biomarkers for Parkinson's and Alzheimer's. So please welcome our speakers today. You may notice that their titles are very long and lengthy. They have earned them. So this is truly a reflection of their astounding careers and also accomplishments and success at MIT. So our first guest is going to be Marzyeh Ghassemi, Associate Professor in Electrical Engineering and Computer Science. She is at the Institute of Medical Engineering and Science, MIT's Computer Science and Artificial Intelligence Laboratory, and the MIT Abdul Latif Jameel Clinic for Machine Learning and Health. Round of applause for her, please. We also have Dina Katabi with the Thuan and Nicole Pham Professor of Electrical Engineering and Computer Science. Welcome. And we're also going to have Polina Anikeeva, the head of MIT's Department of Material Science and Engineering. She is also the Matoula and S. Salapatas Professor in Material Science and Engineering, a professor of Brain and Cognitive Sciences, and director of the K. Lisa Yang Brain Body Center. Thank you all for joining us this morning.
Please welcome to the stage Marzyeh Ghassemi.
Hi, everyone. I'm going to talk to you today about research that I do on ethical machine learning. And a lot of the research that I do focuses on healthcare, but these lessons apply more broadly to every human-facing setting that you might imagine or know that AI is being used in today. So my lab is the Healthy Machine Learning Lab, and we really try to focus on understanding whether AI is needed in a specific situation. If it is, trying to construct the most robust system possible. And then finally, even if you have a robust system, you have to understand how it will be used in context. So looking at the needs in a specific setting. And I want to walk you through an example where we did that, where we were approached by some clinicians in the Boston area, and they said, you know, if somebody is sick and they come in on a Friday night and the hospital is really packed at Mass General, for example, we don't want them waiting around in the waiting room if they're not actually sick, right? So if you're having trouble breathing and I take a chest x-ray, if you're sitting in the waiting room, there's SARS and COVID and MRSA, there's everything in a waiting room. And so if you're not sick, let's just send you home. Can you help us build a triage device? Something that will just look at this chest x-ray and say, this patient doesn't need to wait around, they can be sent home. And so in order to do that, we can run through this pipeline that everybody runs through when they build machine learning models for any setting. You pick a problem, get some data, define your outcome, and then you optimize your model and potentially deploy it. And when we run through the steps of these models, first picking our problem, which we've already done, we want to do chest x-ray based triage. We can then collect data. There are 3 large publicly available chest x-ray data sets in the United States. Check. We can then build our model. Here we build a kind of convolutional neural network called the DenseNet. And then when we optimize to predict no finding, which means the patient is healthy, there's no finding in their chest x-ray, we get a performance. Here we get an AUC of 0.85. That's pretty good. Okay? The question is, should we be deploying this model? And that's not an abstract question because lots of models have been deployed in healthcare and beyond in many different clinical subspecialties. But when we look back at this really fantastic model and think about reasons why you might be anxious about deployment, one thing we can do is not just say there's one number that represents your average performance across all 700,000 of these chest x-rays. We can look at your subgroup performance, and specifically the false positive rate in different subgroups. And a false positive rate here in this setting would be underdiagnosis. Because if I falsely positively say that you're healthy, it means you're sick and I made a mistake and sent you home, okay? And if I look at my false positive rate in this state-of-the-art, published in Nature Medicine, 700,000 examples model, I find that I have the largest underdiagnosis rate on female patients, young patients, Black patients, and patients on Medicaid insurance. And if I look at intersectional identities, I do even worse on those subgroups.
And so what this means is if we want to create ethical machine learning, ethical AI in a healthcare setting, we really need to think very carefully about how we're doing it. And I'm going to walk through actually three stages of this pipeline and give you some examples of how you might do that, okay? The first thing I want to talk about is data, because that's what everybody's talking about these days, right? Think about the data. Why do you need to think about the data? There's a really famous thing that everybody in machine learning knows that maybe you might not know if you're not in the area, which is that machine learning models are lazy. Okay? They use the background to classify images. And so a very fancy model will say that this is a cow and this is a benign mole. But if you take exactly the same object and put it on a different background, suddenly the model isn't sure. It thinks that that cow on the beach is an orca. And it's true, right? I'm not lying. And it thinks that this benign mole is now cancerous because it sees markings and it knows that when doctors are suspicious of a mole, they put markings around it, okay? So it's not always using what we want it to use. Sometimes it's using these shortcuts to make predictions. And maybe these are funny because you can look and visually confirm that it's using this shortcut. But in a healthcare setting, machine learning actually has superhuman capacity. What do I mean by that? I mean that when we train machine learning models to predict clinical things, they learn in their layers other demographic information. And so, for example, if I redact all of the mentions of demographics from a clinical note, doctors can't tell whether this patient is Black or white, male or female, but machine learning models can. And even more scary, I think, is in a medical chest x-ray, which you can see an example of. No radiologist can look at a chest x-ray and tell you somebody's self-reported race. But machine learning models can with AUCs that are almost perfect because they're using high frequency information that is involved in the blocking of some x-rays, right, from people who have more melaninated skin. There's nothing crazy about that, but your eyes and my eyes can't do bandpass filtering of images and then classify the tiny amount of interference that happens. Why is it dangerous that machine learning models have a superhuman capacity to see something that we maybe can't? It's because of this shortcut problem. They can perfectly see a shortcut that we might not be able to. And so we wanted to evaluate how dangerous could this be when we train machine learning models in these imaging settings to predict something clinical, and then evaluate what they learn sort of in their layers about these different tasks. And so when we train models to predict something clinical across all of these different subspecialties, we reconfirmed in a recent work that they do learn your demographics. What's even worse is the more they learn your demographics, the worse they do at predicting a disease within those demographics. Put another way, if I'm trying to predict cardiomegaly in chest x-rays and I learn who is female, in my layers, the more I learn who is female, the worse I will do at predicting cardiomegaly in female patients, okay? And there's ways that you can try to address this. Beloved by all economists, this is a Pareto plot where I show you the trade-off of two things on the X and Y axis. And you can see that if I have on the X-axis overall AUC and on the Y-axis the fairness gap, I want to be in the bottom right-hand corner for any of those plots, very well on average and very low fairness gap. And the nice thing about this is that in each of these different graphs where I'm looking at a different task across different subgroups, you can pick a model that works really well. It's in the bottom right-hand corner, which is great. That means that modern optimization techniques can lead to models that are fair within a context and we would be comfortable deploying. But this is when I trained and tested my models on data from a Massachusetts hospital, okay? Is that how we evaluate models? Not really. What happens is we train and test in Massachusetts and I call my friends at Stanford and say, it's good, deploy it there. What happens when we deploy these perfect models in Stanford and new data in California? What happens is that we immediately shift up and left. And so models that are really good in one setting, even when they're trained on lots of data, when you move them to a new setting, that sort of robustness does not transfer. And so this is a really important lesson if we want to continue to build models on new data. If you're going to deploy your model in a new medical setting, you really have to apply it in this context and evaluate it to the patients it's going to be deployed on. if we think about how these algorithms work and whether algorithms are, sort of able to close this gap entirely, one thing to keep in mind is that apart from data, we've had, these problems for a very long time. So, maybe you're thinking that all of these biases, all of the things I showed you, those are modern AI problems, but they're not. These have been around for decades. And so, in fact, for the past few decades, there's been this really hot topic about whether you should even use a group attribute like sex or age or race in a clinical risk score, and not a modern, big, deep learning model, just a simple logistic regression. And the reason it's a hot topic is because you can use a group attribute in your logistic regression model. And while it is guaranteed to improve overall performance, it can reduce your subgroup performance. So here I built a logistic regression model to predict sleep apnea. And when I use sex and age, it is worse for younger male and older female patients, even though it's 1% better on average. And so the problem is often when we optimize these models, we're either doing this sort of model misspecification where we don't account for all the ways that features and attributes might interact, or we're just telling our model explicitly to optimize for the average. And if that means that they misclassify all 10 female patients in the data set, well, they're a small subgroup. You told me to do best on average. And so there are ways that we can address this in maybe simpler models, but this same problem exists in larger models and becomes harder to scale when we look at debiasing. So if you've ever played with a vision language model like DALL-E or maybe in Midjourney, what you do is you ask a model to generate a photo of a doctor, it runs it through a diffusion model, and then you get a picture. But it's not just for making pictures, you can also do zero-shot classification and retrieval. We use them in all of these different tasks. But the problem is vision language models have been shown in all of these tasks to have extremely problematic biases. And modern debiasing techniques, if you look at a lot of the papers, they make an assumption based on this sort of older mindset that these models are linear. Somewhere in their latent space, there's some place that is male and some place that is female. And if I just can estimate those two places and orthogonalize and project them out, then I'll be fine, right? I can evenly classify or retrieve male and female doctors. But in reality, these sort of latent spaces in a model's mind are extremely complex and nonlinear. And so what that means is if you debias for the male and female direction for one profession, you might not actually do well in other professions. And so the way to move around this is to sort of acknowledge that these models are nonlinear. And so we have new work where that's what we're trying to do. Rather than saying we embed a point that means doctor, and then do the standard thing, which is find male and female, and then move to this place in this linear estimate, we instead say that's not going to work. Because here, I'm still closer to these images of male doctors than female doctors anyway, because this is a complex nonlinear space. And so what I really want to do is use this as a starting point and move along this nonlinear boundary between these two groups until I'm at an equidistant spot between these samples. And so we want to use the actual topology of this latent space to get what we want, which is this even retrieval rate. And, this is a sort of nice approach because it's really emphasizing that you can do it at test time to improve both classification and retrieval rates. But I want to say one last thing about, this all seems great. You may have noticed a theme, right? I say it all seems great, and then I hit you with something else. This all seems great. But what about something really simple like negation? Why does negation matter? Because despite their flexibility, vision language models really struggle with negation. What do I mean by that? If you ask a vision language model to give you an image of table with no chairs, it'll give you a table with chairs. And this is not just true in this example, it's generally true for image generation. It's also true in image retrieval and in visual question answering. Why is this happening? Well, I'll tell you in a minute, but first you might think again, like the cow on a beach example, this is funny. It's not funny in medicine because if I say that I want to retrieve evidence of lung opacity, I want this image. If I want evidence of lung opacity with no signs of edema, I don't want this image. And so the confusion is no longer sort of an interesting feature, it's a huge bug. And the reason that this confusion exists is because how are vision language models trained? They're trained on all of the internet. all of the images on the internet and the text that describes them. What does all of the images on the internet looks like? It looks like this, right? Vision language models are trained on captions that describe what is present. We don't, for example, say that there's a black and white dog jumping over a bar. No helicopters, though. That's not how you describe text. And yet, that's what we're asking a model to be able to generalize to know what the absence of something means when it's never seen an example of what that might mean for mapping between text and an image. And again, this is even worse in a medical setting, because in a medical setting, you often say what the sort of medical problem is, and then say a whole list of things it's not. It's not this, it's not this, it's not this. Okay? And so we wanted to see just how bad this is. And to do that, we had to make a data set. Okay, so we made a new data set that has lots of examples of negation: simple negation, hard negation, and medical negation. And what we found is that when you use simple negation, state-of-the-art vision language model performance drops by maybe 4 to 7%. When you use hard negation, state-of-the-art vision language model performance drops by 18 to 22%. When you look at medical vision language model performance, negation drops your performance by 30% or more, which is very scary, right? Because these are state-of-the-art models that are currently being used. And if you want to understand maybe intuitively what's happening here, what's happening is that when I map all of these objects into this model's latent space, again, this mind map, you can see that if I say something is a dog, which would be a certain color in a circle, or something is not a dog, which would be the same color in a triangle, the colors are very close to each other. That means it's not a flower is very close to it is a flower. And if you look at even more modern models that are trained specifically to understand negation, what they do instead is they map the negation of everything, every triangle, to that red circle. That's not a flower, not a dog, not an elephant, not a train. And that's not what we need if we want these models to sort of extend into machine learning spaces where humans are present. I want to talk briefly about deployment by not walking through this example, given the amount of time that I have. So you can see there's lots of fun research. But I want to say, if we want to transform AI and improve human lives, we need to realize 3 things. The losses that we can get from poor AI are much larger than the gains from good AI. And so the first thing to realize is your model has to be good. So test it. The second thing is we know humans are susceptible. Lots of good research has shown that, even experts. And so make sure you evaluate your model comprehensively on different kinds of people. And finally, we have lots of work, so do other groups, showing that advice might be good or bad. The way it's delivered also matters. And so make sure that you're not convincing people to do things that are inappropriate when your model might be wrong, because it will be sometimes. And by doing that, we can focus on moving forward with ethical AI and human health. Thank you.
Please welcome to the stage Dina Katabi.
Hello, everyone. So I'm going to continue the theme talking about AI in health. However, before starting, I want to note that we check all subgroups and we have IRBs and informed consent, everything to ensure ethics are preserved. Okay, so let's start. So I want to talk about ambient AI for home health. So one of the key problems today in medical systems is that medical data is both scarce and also is episodic. Typically, we collect medical data after the fact. Somebody is suspected of having cancer, so we go have mammogram, have PET scan, have stuff, or tests. But that is after something bad happens. And this fact that we are unable to track in real time changes in the health of individual causes problem across the all of the stakeholders in the medical system. Whether you are talking about care delivery and healthcare, I mean, medicine is reactive instead of being preventative because we don't really know what's going to happen. We don't have data for today, it's only after the fact. Also, in terms of like pharma and biotech, they are in the business of developing drugs and therapies, but they collect few data when somebody comes to the hospital or the site. And many, 90% of the drugs and clinical trials fail. If you talk about people like many of us who are family caregivers, who's like taking care of mom or dad, have no clue. I don't live with my mom and don't know whether like she's doing well now, like how is her health? Is there any problem? I have no idea. So how can we transform all of that? Imagine if we can have an AI companion that lives in the background of a patient's home and from thin air can collect dozens of physiological signals, breathing, heartbeat, mobility, posture, sleep, EEG, all of that stuff without touching the person, without anything. People live their lives. And this is exactly what we have developed. We have developed a system called Emerald that is like, it's an AI system that understands human physiology and actually understands it from thin air. So we have a device that looks like your Wi-Fi box. It's sitting in the home, and it's analyzing the wireless signal that bounce off people's bodies because our bodies are made of water. So when wireless signal touch the body, it reflects. And it has all of this information about respiration, movement, everything. In fact, our recent thing can get even the EEG of the person. And from that, we get these physiological signals, and also we get an understanding of how the disease and the medications are affecting the person. So I'm going to show you a few videos from, this is one of our earliest results. So here you see one of my students. This is one of our MIT officers. We are going to monitor him from behind the wall because wireless signal traverse walls. And you see that dot on the floor. Now, if I play the video as he moves, you can see how the dot is tracking him. He has no sensors on his body. He can just be completely oblivious and just live his life, and we can collect his movements and understand how his speed, his balance is changing over time. Now, of course, everything that we do, we compare to the gold standard, and we publish it in peer-reviewed conferences and journals. So this is, as I said, one of the early results. Today, we can actually, it's not a dot on a floor map. We can get the full skeleton of a person. And like when he sits, you know he's sitting. When he stands, we know that he's standing. He moves with the right foot. We know the right foot, the left foot. All of it using wireless signal and without having cameras, without having anything in people's homes. Not only motion, we can actually, like when we go to sleep, our brain waves change and we enter different stages: awake, light sleep, deep sleep, and rapid eye movements, REM, which is the state during which we dream. And today, if you want these sleep stages, of course, sleep stages, 1 in every 3 Americans has sleep problem, but actually it's much more important. Sleep is a platform for all diseases, whether you are talking about Alzheimer, Parkinson, depression, or immune diseases, everything affects and interacts with sleep. So today, if you want accurate sleep stages, you send someone to a sleep lab, they put these electrodes on his head and body. Yeah, he wasn't happy. So let me show you what we do. So this is our Emerald device, transmits very low power wireless signal, analyzes the reflections with AI, and spits out something called a hypnogram. For every 30 seconds of sleep, it knows whether the brain is in light sleep, in deep sleep, in REM, etc., as our brain moves between these stages. And again, everything is compared to the gold standard. And in the case of sleep, it's something called PSG, which is like all of those electrodes on the guy's head and body. So this person is sitting like you, and what you see on the screen is his inhales, exhales. He doesn't have any sensor or wearables. We asked him to hold his breath. You see the signal stays at a steady level because he exhaled, he did not inhale. And over the last few years, we actually started a company, and we started working with pharma and biotech who use our technology, our AI technology, for understanding diseases and new drugs in their clinical trials. So we started deploying these devices with patients in many clinical trials, like people who are developing drugs for ALS, for Parkinson's, for Alzheimer's. And we collected a huge amount of data that added to our ability of understanding these diseases and these therapies. So as a result, like one of the things that we started like moving toward, not just like physiological signals, but can we understand diseases better? And I'm going to show you two quick examples. So Parkinson, for example, is a disease that is the fastest growing neurological disease in the world. And Parkinson, of course, we all know it from the tremor and the stiffness of motion. But one of the problems with Parkinson is by the time it gets diagnosed, about 50 to 80% of the neurons in the brain, the dopaminergic neurons, are already damaged. So you have a disease that you are diagnosing at a time when most of the relevant neurons are damaged. So people want to diagnose the disease early, but the problem is that the motor symptoms, the tremor and the stiffness, happen later, and by that time it's too late. So we asked, can we diagnose Parkinson without any motor symptoms? So can AI detect Parkinson from breathing, how people breathe during their sleep? And so we trained a neural network that takes this respiratory signal. We know that we can get breathing from people. I just showed you from thin air, from wireless signal. And we trained the neural network to answer two questions. Does this person have Parkinson? And if they do, what is the severity of their disease? And this is a large study which have like more than 7,000 patients, 7,000 individuals, 700 of them have Parkinson's. And let me show you the result. So these are standard curves that we use in machine learning. On one axis is specificity, on the other one is sensitivity. Now, if you haven't seen this, the important number is this AUC, the area under the curve, which shows you that you can interpret it as accuracy. So with an accuracy of 90%, we can tell from the wireless signal bouncing off people in their home whether they have Parkinson's or not. And we are still, of course, there is so much work that needs to be done yet, but we have an initial study that shows here that we can even tell that somebody has Parkinson before it is diagnosed. So the people in blue, and like basically the people in blue developed Parkinson's about 6 years later than we have this data. And you can see that the model already shows that they are very different from the people in red who did not develop Parkinson's later. Mental health. Mental health today is just an art. I mean, doctor gives patient drugs and say, how do you feel? I mean, the patient say, oh, like I feel better, I feel worse. And it's like, we know that many of it is placebo effect. And it's the person, okay, don't feel good. I mean, okay, let's wait, maybe you will feel better. And we just have these trials. There is no actual test for whether the antidepressant is affecting this patient that I'm giving the medication to. So we asked whether we can do this completely passively in patient's home. We trained a neural network that takes, again, breathing signal and asks the question, is this person using antidepressant? Because if we can tell that from their breathing that they are using the antidepressant, it means that it changed their physiology. So here are the results. So again, you see the AUC. I told you the AUC you can interpret as an accuracy. So from one night of data, we can tell with an accuracy of about 86% that this person taking antidepressant or not. And you can see like the table shows you a variety of different drugs. In fact, for the common drugs called SSRIs, we have even much higher accuracy, about 90+%, 98 sometimes. And these are two examples. The first one is a person who, like the x-axis is time, the y-axis is the model prediction. And there are two examples. You see one person who was not taking antidepressant, then he took antidepressant, and you see the model moved from, no, he's not taking antidepressant to like, okay, he's now on antidepressant. And the opposite is somebody who was taking antidepressant were taken off the drug, and you can see that the model knows that this has happened. So let me finish with saying that we imagine and we envision that the future AI can help a lot understanding diseases, understanding drugs. And with Emerald, like we are like trying also to move that to translation phase so that we can make it available for the healthcare system. We envision a future where these kind of Emerald AI systems are in every home, same way as we have a smoke detector in the home. We probably would agree that we would want to have something in the home that monitor the health of the family, like if there are problems, be able to detect them very early on and alert people and be able to deliver personalized health in hopefully soon in the future. Thank you.
Please welcome to the stage Polina, Anikeeva.
Good morning, everyone. We are going to take a dramatic switch in terms of discipline, and rather than talking about beautiful algorithms, we are going to start talking about hardware that is ultimately needed to perform interventions, even if you have excellent data, as well as hardware that you need to acquire that kind of excellent data. And I'm a material scientist. I'm also a brain and cognitive scientist. And what ultimately brought me to the study of neurobiology is this incredible beauty and complexity of our nervous system. In this wonderful image taken by Kwang-Hoon Chung, who's now a professor at MIT, you can see different colors, and those different colors represent different types of cells in a portion of mouse brain. And those different types of cells communicate through a variety of different types of signals that come together to make us who we truly are. Now, how do we record this wonderful diversity of signals? We engineer hardware. And that hardware typically comes to us from the field of electronics, semiconductors, microchips, and so forth. And those technologies can be quite powerful. You all have one in your phone, in your computer. There's one problem, however. If we take a look at them from a material science perspective, you start noticing something distinct. All of those tools are hard, they're brittle, they're sharp, they have nothing to do with the physical properties of the nervous system, which is soft and squishy. And when we take a device with mechanical properties of a knife and we stick it into the brain with mechanical properties of a yogurt or a chocolate pudding, you can imagine what happens every time you breathe. You take a step and your device moves. You're cutting through the very tissue that you're trying to probe. So how can we engineer a better device? We can draw inspiration from nerves themselves. Those are soft, they're flexible, they can transmit a variety of signals, not just electrical, but also mechanical, thermal, chemical, and they span from microns of our cells to kilometers that span of the nervous system within our body. So how do we create an artificial nerve? Here, we steal and borrow from the world of photonics and telecommunications. All of you are familiar with fibers that are made of glass that go underneath Atlantic and Pacific, allow you to make calls to your friends, and, for example, in India, as our MC probably frequently does. But now, we can make those fibers not only out of glasses, we can make them out of a variety of materials, including those that are soft and flexible, just like our nerves. So how is the fiber made? Just like any normal glass fiber, our fibers start on the macro scale. We envision our perfect imaginary nerve. For example, we want transmission of optical signals. We will add a transparent optical core and a cladding. We would like electrical signals. We will add conductive elements of a composite or a metal. We would like to deliver drugs. We can leave holes, channels in our device. We do it all in the machine shop. We create a structure that is in the order scale of inches. Now we take this structure, we term it a preform, we heat it, and we cool it. And the features that started out as inches become microns, and we get kilometers of soft, multifunctional fiber that mimics nerves. With these kind of devices, we can now perform interesting experiments. Here in the mouse brain, we can simultaneously stimulate neural activity. You can see those blue pulses. We can record neural activity. You can see spikes. Those are action potentials. And now we can infuse a drug, this pink rectangle. And that drug is inhibitory. And you can see in real time as activity starts to go down, and as then the brain starts to wash that drug out from the system, the activity begins to recover. So now we have a platform to be able to test the effects of drugs, the effects of stimulation, all in real time. And of course, this is possible not only in an anesthetized mouse, it's possible in behaving animals that perform tasks. So now we can use these platforms also to make correlations between neural activity and behavior. But it's not all about mice. Can this technology eventually become something that serves human patients? And when we think about serving human patients, the key challenge that we actually have to confront it is quite prosaic. It's scale. The size of the mouse brain is about the tip of your thumb. The size of the human brain, put your two fists together. That's it. That's your brain. Yes, admire it. That's about the size. Now, if you designed your perfect device, let's say that you're fabricating on a wafer, like a typical semiconductor device. If you designed it on a millimeter scale for a mouse, when you start to scaling to inches or centimeters, you have to start over. The processes are completely different, except in the case of a fiber, because fiber is drawn by kilometers. So now the same device that we can rigorously test in a mouse and know how it works and that is safe, if we want to deploy it in a translational animal model or in a human patient, we simply cut it longer. If we want to make one for a giraffe or an elephant, we can cut it longer. So now, here you see an example of one of the same device, one made for a mouse and the longer cut deployed in a non-human primate, our closest relative. Now, because this device is safe, we can actually deploy it in this complex and sophisticated research partner, non-human primate. And for the first time, we're able to record neural activity and then modulate it with a drug, in this case, inhibitory drug GABA, in an awake behaving primate. We can see how the brain responds to different concentrations of this inhibitory drug and how the activity is blocked for different amounts of time for different concentrations. So now we know that we can have devices that are quite powerful for recording stimulation of neural activity in the brain. So far, as neuroscientists, we have considered the brain as this wonderful deity that stands alone and floats in vacuum. But good news, your brain is actually attached to your body. It's part of your body. It's not, it's a biological organ. And for us to understand how brain works and how it connects to the body and how it influences our conditions and how it becomes diseased, we need to be able to connect it to the body through our understanding and have holistic understanding of our organ systems and how they support the brain and interact with the brain. And I will give you specific examples of one of such interactions across brain and body. And that is interaction between your brain and your gut. So all of you know that there are about 100 billion neurons in the brain. But how many of you know that there's 1 billion neurons in your gut? There's a nervous system in there. What is that nervous system doing? That's a good question. And why do we need to know what that nervous system is doing? There's quite a few reasons. For instance, 8 out of 10 Parkinson's patients are diagnosed with constipation decades before they start having motor symptoms. 9 out of 10 autistic individuals would have severe GI dysfunction. And also, anxiety and irritable bowel syndrome share genetic risks. Are those coincidences or are those correlations or causations? So how do we can begin answering those questions? And how can we begin connecting across this gut-brain divide? We have developed neurotechnology for the brain. How about the gut? The gut presents a whole different slew of challenges. Unlike the brain that moves microscopically, the gut is in continuous motion. It's continuously deforming and stretching. And the nervous system of the gut is like two stockings within a very thin wall of the gut. And if we damage that very thin wall, we can cause severe immune reaction and actually sepsis, which can be deadly. At the same time, the gut lumen is full of contents, and those contents are not nice. So how do we engineer for a system that is so delicate and at the same time so harsh on our electronics? For that, we had to completely rethink how a fiber is designed. Now, we can create a device that not only is flexible, but is also stretchable. But the features that are functional features are no longer just thin elements going along the fiber length. Instead, we borrow commercial and mature microchips fabricated on a really small scale in the semiconductor industry, and then we scatter those elements across our fiber length, such that our sensors, such as, for example, detectors, temperature sensors, chemical sensors, here you're seeing light-emitting devices, those sensors are now scattered across the length to match the gut anatomy, and at the same time, they're looking at the gut wall instead of looking down, where they're not going to be seeing anything particularly exciting. So now we have these microelectronics-enabled fibers, and because all the components are inside, we can also begin operating them wirelessly. That gives us an opportunity to do much more complex behavioral experiments with all of those different elements. Here you're watching LEDs blink, but of course we have a variety of other sensors that don't look nearly as fun in videos. But now, if we're going to have a device that can work in our gut, what should be the first test? How can we know that this device actually works for what we designed it for? Well, if it's the gut, and we can ask some simple questions, and in the context of our GI function, those simple questions will likely have to do with food, and particularly our preferences for different types of food. And we are going to talk about sugar. All of you had an opportunity to choose what kind of sweetener you're going to put in your morning coffee as you were all networking this morning. And you all chose either real sugar, sucrose, or fake sugar, sucralose, such as Splenda. Well, it turns out that unlike you, mice are not fooled by those choices, and they exclusively go for real stuff. However, now if we take one of our fibers and we implant it in the mouse gut, and then we are going to use its stimulation features to block the activity of sensory cells that can differentiate between molecules of sugar or sucralose, Splenda. If we now block these sensory cells, our mice lose the ability to distinguish between those sugars. And it has little to do with taste. It comes from your gut, and it takes milliseconds. So your gut is not fooled either. Maybe you have convinced yourself that you like Splenda, but you have not convinced your sensory cells. Well, okay, that's the food. Can we do something more exciting in the context of this gut-brain interaction? And what can be more exciting than happiness? Typically, we think of happiness in neuroscience as release of dopamine in a particular brain region called ventral tegmental area. And how could we test this happiness state in a mouse? We cannot ask them. So what do we typically do is we actually give them this box with two compartments. And in one compartment, we are going to do nothing. In another compartment, we can conduct some kind of stimulation. For instance, we can excite dopamine neurons in the brain to produce dopamine. And when that dopamine gets produced, mice begin associate this chamber, this part of the box, as with the happy place. And that's where they stay. And that's a Neuroscience 101 experiment. It's very classic, very robust. We can do it with electrical stimulation, drugs of abuse, sugar. So those are all very classic experiments. But now we're going to conduct a different experiment. We're going to leave our brain alone, or mouse brain alone. We're going to put them in a box, and instead we're going to stimulate the nerve endings in their gut. And what do we find? Is the same state of preference or happiness. Now we're able to control this choice, this complex behavior through the gut instead of the brain. So now you can think about what kind of implications it has for treating affective disorders, such as depression. Rather than manipulating someone's brain, we can have a more holistic approach and tap into those gut-brain circuits at the level of our peripheral nervous system. And that's just the beginning. Every organ in your body is innervated. Every organ in your body talks to your brain. And maybe by using these bioelectronics, we can begin tapping into that innervation to achieve whole human health for conditions that we have previously only thought of as affecting our brain or the organs. I have to thank all of you for allowing me to present this work, and of course my extremely talented group of trainees and people who support us. And I also have a disclosure to make that the technologies that I have shared with you is starting to translate from methods to cures in human patients, in part through really fantastic programs such as MIT Future Founders that allowed my trainees, MJ Antonini and Nikki Driscoll, who is a female CTO, to take this technology and now start to use it to treat stroke patients. So thank you all. And with this portion of our program, I would like to invite my colleagues back to the stage for the Q&A.
Ladies, so much. That was incredible. And I think everybody here will agree we could probably do a whole day session just hearing from each of them and what they're working on. So thank you so much for sharing that and your research. And I have to add just a personal note. I think that everything that you've talked about is so timely. Like, we're living in this world and this time where we have to be aware, especially what's happening for women and, bias and healthcare, and actually owning how we sort of move forward with the knowledge. So thank you again for sharing that. So what we're going to do for the next session here is actually ask the questions that all of you have sent forward. So thank you. And if you haven't already, use the QR code in front of you and go ahead and submit questions for either of our speakers. We'll try to keep on track because we are running a little bit late, and we want to make sure that you get a chance to have your networking break, get a chance to actually get a time with each other, and then also leading to the next session. So we've got a couple of questions here for each of you from the audience. We're going to start with Marzyeh. So you talked a lot about what's happening with accessibility, equitability, and also accuracy of the data. So what are the biggest challenges for you as a researcher right now that you maybe want to highlight, or that you're sort of aware of as we talk about accuracy? Like, how do you ensure that we actually have the quality that you're looking for?
There's maybe two things to think about. So the first is when we think about healthcare specifically, unless you're running a prospective study where you're carefully collecting labels, right, as my colleagues are doing here, a majority of the machine learning models that operate in healthcare that maybe you've seen offered as a service by companies, both by large tech companies, but then also by medical records providers like Epic. They're using all of the historical data that exists in the medical record, for example, to train a model to recreate exactly that. Has anybody here been to the doctor recently? Was it perfect? Do you want that to be encapsulated, crystallized as the service and care you'll get forever? Well, that's what's happening right now, because the data that's being used to train models forever and ever, right, is this historical data, right? And it's not also data from only potentially, a doctor when they're at their very best. It also includes doctors on the night shift, doctors who are making mistakes, doctors who haven't slept in a while, right? Nobody's going back through those records and picking out the ones that shouldn't be used, right? Because that's a liability risk. And so I think one thing we really need to understand, just like the negation example, where, well, of course the model doesn't know how to match a caption with a negation in it to an image. That doesn't exist on the internet, right? Like, we don't describe images that way. If we want machine learning models to only extrapolate the very best care, we should probably show them that, right? And right now we don't really have that. And so I think creating new data resources and being conscious of the fact that that is not what we get when we dump an EHR system is, I think, how we can move forward.
Yeah, thank you so much for that. And I think that sort of ties into the next question, which is also then around predicting race, right? How it can still lead into like the worst outcomes, how we sort of manage that. And maybe also just share, what would you like to see in those prediction models then versus where we are today?
I think one thing that's very important is that we think about what protections we want as a society for everybody, right? No matter who you are or what you look like. And in the United States right now, so far, we have some laws on the books that guarantee, for example, civil rights laws that people have an equal right to education, RIP Department of Education. Or that people, for example, have equal access to financial services, right? There's a fair lending law. Men and women are supposed to have the same access to loans, right? Recently, there was a section of the Affordable Care Act that was finalized to say that for the first time in history, any algorithm you use in healthcare is supposed to work equally well on all people. That didn't exist before. That just happened last year. So if a doctor, you may be aware if you've been to a doctor, right? If a doctor does a bad job on a patient, there's no sort of federal reporting structure that makes sure that they're not routinely doing worse on certain kinds of patients, right? And so for the very first time, codified into law in this new section 1557 of the Affordable Care Act last year, we have this rule. Well, algorithms can't do worse on different kinds of people. But there's also the threat that this is going to be repealed. This has been stated several times by the current administration. And so I would say, regardless of what your views are on, administrations more generally, everybody deserves to be able to go to the doctor, to be able to use the healthcare system and not be afraid, right? And so we need to ensure that, these kinds of laws, these kinds of efforts are on the books and are being enforced, because otherwise they won't be, and they historically haven't been.
Mm-hmm. Yeah, and you bring up such a great point too around, I think, maybe what we are able to do and what we're aware of. So literally everybody in this room, and I'm going to sort of adapt this next question. So false positives, for example, right? So you're aware of it, you're seeing it in your research, but how does it sort of compare to then how the doctors are using the information, right? And what should we maybe also know for ourselves as we get into this era of, you're going to probably work with a provider who's in some way, shape, or form leveraging AI?
I think there's, what you can do, and that's largely, sort of predicated on what you know. So I will say, as a personal story, right? I have a daughter who it was recommended that she get treatment, right, with one of the hospitals here. And they treated her, and then they wanted to continue to treat her. And I said, well, you haven't really told me why you want to continue to treat her and up her treatment. And then, we had several follow-up sessions where they would say the same thing. We want to up her treatment. We want to up the dosage. And I said, well, you haven't really given me any evidence. Where are your papers? Not a very compliant patient, advocate here. And I looked at the medical record, and I noticed that they had written several times in the notes, The mother is not compliant. She is aggressive. She is. I think they like the language. She's difficult, right? And I had a phone call. I then scheduled. I sent an email, copied all of the clinical team. I sent an email, and I cited my own papers in the email. I cited my own papers in the email, and I said, just so you know, I know your hospital is using AI to look at patient notes and then make predictions about who should be given double bookings, who should be given referrals, who should get access to different resources. I know, I can CC your CTO if you want me to, but I happen to know this through collaborations. I also know that you have written these things about me, and I wrote out the portions of the record where they had written it, and I said, I also train and audit algorithms exactly like the one you've deployed that will use these sentences you have written to provide worse care recommendations for me and my family. I want them changed. And there was such a negative reaction. And that's sort of a funny story. But also think about, somebody who is maybe undergoing cancer treatment and is being described that way, and they get labeled as non-compliant. Well, if you need an organ someday, as many cancer survivors do you know what automatically puts you at the bottom of the list for an organ? Non-compliance, drug non-compliance, because they think you won't take your anti-rejection medication. And so we're making all of these decisions about using AI, in these really like efficiency, automated ways. And those are really driven by business decisions. They're not being driven predominantly by doctors and real needs of real patients in care settings. And so I would say the best way to sort of, ensure that you're not being mistreated is to be aware of how you could be mistreated and then advocate for yourself, even if you're described as difficult. Yes.
Thank you for that. So I guess to sort of summarize, go ahead and ask the questions, find out what they're doing with the data, how they're maybe encompassing it, and maybe also take a look at your report and be called difficult, right? That's the worst case
It's
scenario.
okay to be difficult. What's wrong?
Thank you for that. Okay, well, just for time's sake, we're going to move on to Dina. So for Dina, the first question that we have here is, what's the biggest specific challenge that you have faced in developing the wireless sensing and AI technologies for healthcare? And how did your MIT research help to address it?
How is MIT research what?
So what's the biggest specific challenge that you have faced in developing the wireless technology? And then how has your research actually helped to address it?
I see. So I think the biggest challenge in healthcare today is the status quo. It's not like technology or technical or even with all of the risk of AI. I think the problem, and it's not news to anyone that the healthcare system, the incentives are all in the wrong place, like between the payers, the providers, and like the interests of the patients. And even within these groups, like there are subgroups of completely different interests. And as a result, we spend so much money and resources on things that do not lead to better outcomes. For example, like providers, for example, they are paid by procedure. So upping the drug and doing more like procedures is how they are paid. Even when you have the at-risk provider, it's very hard to assess risk. In fact, you get more risk or you get paid, like how like healthcare is like fee per service and fee per value. But even with these capitated model, like you have incentives to make people have as many diagnoses as possible, because then that particular person becomes more, you are paid more for that particular person. It's like there's so much there that it's like how we can improve the healthcare system is really limited by much of the structure that we put in that system that has nothing to do with medicine or technology or science. The other thing that it's important, I think, is basically reluctance to I mean, with all of the caveat that Marzyeh said about AI, actually AI, its biases actually are in front of you. You can test the biases, you can counter the biases. There are algorithms, there are ways, and when we at least you can test them and say these are the biases, don't use this algorithm in this particular way. But human biases are very big and much bigger, and they are not testable in the same way, and you cannot really deal with them in the same way. So there are many challenges in the healthcare system. Unfortunately, the challenges in the US, despite the fact that we are like quite advanced nation, are much bigger than in other countries where like there is one healthcare system at least that has at least clear incentives for its patients. So that I think is the biggest challenges. Now, in terms of technical challenges, I mean, of course, these are like what we call hard tech. So it's so like, for example, like for me, like trying to take and translate that technology to something that I want to see being used, being able to help people. I wanted to, like, if you go like down the standard path of like creating a company, like this company, hard tech company, takes much longer time and much more development. So one of the things that we had done is to start the company completely from revenue, like completely organically, with like without investment, to just like grow the company with pharma and in clinical trials to allow for the company to address the need of the technology and the development before thinking about scale. So that was one of the challenges in terms of like how do you do entrepreneurship with hard tech. How MIT has been helpful? I think MIT has the best help MIT provides to any professor and any scientist and any researcher is the students. We have amazing, amazing students, access to like the best brains in the world, and that nothing like can compare with that. I think MIT has been also very, very nice and encouraging in terms of like basically focusing on, like when we talk in many other universities, you talk about, okay, how many papers do you have? Like how much money did you bring? But at MIT, we talk about impact. We talk about like, okay, so what is the impact on the world? What's like, what are the contributions? So that mentality has been helpful. Also, the fact that entrepreneurship also has been like a topic that was encouraged in recent years at MIT. So there are, I can't complain too much because many things are really good, but I think there are also opportunities for improvements on all axes.
Yes, absolutely. Thank you for that. So again, just being mindful of our time. So I'm going to hop over to Polina. So Polina, the next question that's come in here is around sort of, insurance and, compliance and liability. So AI's promises are obviously impressive, but what are your thoughts around sort of ensuring it's not misused by insurance companies, right? Also, just thinking about the discrimination against certain patients who may require expensive care in the future.
So this is a very challenging question, given the fact that I'm a blue sky engineer rather than an expert in compliance, and that's why I let my students to start a company instead of me doing that. So when we are thinking about implantable devices, there are codes, insurance codes that allow for reimbursement for those devices. It's a lot of the challenges in deployment of implantable tools currently span from the fact that they are considered the last resort therapy rather than potentially the first resort where they might need to be. And because of that, this is essentially the last thing that people are going to try when everything fails, and in many cases, it will be too late. So to be able to overcome some of those challenges, our actually technology need to be better, and it's a combination of the technology development itself as well as the surgery. So if you can create a surgery that is less invasive, that requires less of a sophisticated team, then you can go through a much simpler approval process, much less expensive approval process, and then open up much broader reimbursement kind of code portfolio, which is something that is what the company that came out of my lab is doing, Neurobionics. The surgery that they're proposing normally would be a neurosurgery, but instead they're able to do the same procedures through a catheter-based intravenous procedure that can be done in a catheter lab through a simple, essentially, injection device. Does not require a neurosurgeon, it requires a radiologist, and as a result, it just becomes a very different level of reimbursement. And that's kind of an example of how this can be solved through engineering controls, the MIT way.
Thank you for that. And so just to follow up, the next question is around sort of like the implantation. So how can these bioelectronic devices be implanted and powered for long-term use in the body? And how can the data collection become less reliant, perhaps on the wires over time? So sort of like the map and the future sort of those devices.
So it's really, again, those are real engineering challenges. So there's many ways one can deal with powering the device. Of course, Dina is a much more of an expert in power transfer. So far, because we worked with small rodents, it is easier for us to work with batteries, which can be rechargeable. However, whenever you're working with a human, all of a sudden, it's a large animal, and humans actually can carry a somewhat of a larger sort of circuit pack, which means we can do wireless power, and we can easily do recharging, and we can rely on wireless transmission across normal channels, not just necessarily low energy Bluetooth, which is what we have to use for rodents, because of dimension reasons. So you have a lot more options once you have sort of bigger size becomes available. And in terms of the data transmission, we don't actually need to be wired. This all can be done wirelessly. And once it's is done wirelessly, the key challenges is, of course, data security. And at this point, I will have to collaborate with our data security colleagues to make sure that that's embedded within the circuits that interface with our hardware.
Thank you for that. So maybe just a more general question, and I'll pass this to Dina. We obviously have a lot more to learn about each of your areas and the sectors of focus here. What would you like to share maybe with the audience just in closing? Is there a takeaway or something that you'd like them to sort of keep top of mind as we enter this new era? There's a lot.
No pressure.
I think it's so I'm an optimist, like when it comes to technology, and cynical when it comes to people, unfortunately.
Balance.
But I think there is so much to be optimistic about technology. I mean, we keep hearing about AI brings problems and ethics, and these are like, actually it's good to have problems. It means that we have advancement. There are things that we are bringing that can make impact and can make life better, and we just need to, like everything in life, to think about how to bring these technologies to people's lives. I think the future can be really interesting. Like we are living at least an exciting times, regardless of your position on them. But there is a huge opportunity to have better future for everyone. I hope that we don't lose that opportunity and we don't transform it to a better future for the elites only.
Agreed.
Thank you. Well, I think that's a great note to end on. Thank you so much to our guests here.